Hello everyone, it's Mr. Kennedy here. We're going to have a look at the SpaceX mission which successfully took people up to the International Space Station. This was the first time this has been done by a commercial organisation, so it's a really important milestone in space exploration. We're going to look at a particular part of the Dragon module, and that's the launch escape system, which is a really interesting feature of this design. And what we're going to try and do is we're going to link this to the equations of motion that you've been learning about in the higher physics course, and this should allow you to see a real life example of how these equations of motion could be used. So on the SpaceX website, you can get some more information on the Dragon. There's a nice image here of the top section. So in this bit here is where the crew would be seated, and this bit here is where a lot of the cargo that's been delivered up to the International Space Station would be stored. And this all sits on top of the rocket, and we have some data here about the cargo, about the craft itself. So the mass is about 6,000 kilograms, so not too heavy, and it's got a height of about 8 meters.
6, 5, 4, 3, 2, 1, launch. Engine shut down.
Slightly below nominal. We're over 1 kilometer. Chunk deploy. Towards the pit.
So this is a test that SpaceX carried out on their launch escape system, and it was from the
Downrange distance.
launch pad. So you can see the engines fired to accelerate, and it was a really big acceleration to get it away from the rocket in the case of any sort of emergency. And now you can see that the parachutes have been deployed to really decelerate the capsule and slow it down so that it can land safely on the water. So we'll see it landing on the water reasonably soon. So this system is really designed to protect the people that may be on board this spacecraft in the event of any sort of emergency. The most dangerous part of the spacecraft is the rocket itself, because it's full of fuel which is burned to allow it to take off. So if there is any sort of malfunction, then this capsule can separate itself from the rocket. So there are no people on board this one. This was unmanned. It was a test, but it really worked well. And that's it, splashed down. And then there's a boat would come and collect this. It would be on the scene really quickly to rescue any people who are on board. Okay, so in this video, this is from another test of the whole system. I've really just picked out the key bits. We've got the launch and the system itself initiating the parachutes and then the landing. So here's the launch of the rocket itself. You can watch the full video here at this link, but it is about half an hour long, so I have just picked the key parts here. So the rocket launches, and if there was any sort of malfunction with the rocket, then the launch escape system would activate. So that's what you're seeing here, is that the capsule, it's not quite happened yet. I think it's just about to happen. There we go. So the capsule separates from the rocket itself. It accelerates away from the rocket, and then you'll see in a second the rocket has developed a serious problem because it explodes in a ball of flames. But the capsule is now a safe distance away from the rocket. So the capsule has would have people on board. There's no people aboard in this because this was a test. So remember, there were two parts to the capsule. So what happens is they get rid of that lower part that doesn't have any people on board. So that should be happening in just a few seconds. So there we go. So there's the trunk being released. And then the video will skip ahead and we'll look at the parachutes that are launched to decelerate the capsule to a safe speed for landing. So there we go. So again, we've got forces involved here, air resistance, trying to counteract the weight of the capsule. So we have initial chutes go up first and then the main chutes launch. This is the picture here of the main chutes launching, which slows the craft down even further. So they slow it down in stages. And the spacecraft itself, although this one wasn't at a really high temperature, there'll still be a lot of friction, a lot of air resistance, which will generate a lot of heat. So the capsule itself is designed to be able to withstand really high temperatures. It has to be able to withstand cold temperatures when it's out in space, but also really hot temperatures when it re-enters the Earth's atmosphere. So again, the angle that it enters is really important so that it's protected from that heat. So we'll see in a few seconds that it's going to land on the water. Almost there now. And that's it. Splash down in water, and you'll see how quickly the boat arrives to make sure that the people inside the capsule would be okay, although there were no people in this particular one because this was a test, but they're really seeing how quickly they can get the people out of the capsule. So this whole system is really designed to essentially save the crew if there's any sort of emergency. So it's a real safety device, but it's a really interesting feature of this particular SpaceX design. So following the test that you've just seen, SpaceX actually released some of the data from that test. So the capsule was traveling at approximately 540 meters per second in an upwards direction when the launch escape system was deployed. This increased the speed to 670 meters per second in approximately 7 seconds. So I'd like to try and do 3 things. I'd like to calculate the acceleration of the capsule following the deployment of the launch escape system, and I want to assume that the acceleration was constant. I want you to calculate the distance travelled by the capsule during the 7 seconds. Again, assume that it just continues to move vertically. And then the final thing I'd like to do is calculate how far the capsule is from the rocket after 7 seconds, and assume the rocket continues to travel upwards at a constant speed of 540 meters per second. I'd like to pause the video here and try the calculations for yourself using the equations of motion. The solutions will be towards the end of the video, so you can have a look at those once you've tried them for yourself. So here's my solution for this question. So I've chosen up the way to be positive, just because the capsule is moving in an upwards direction. And then I've written down my suvat here. So S we don't know anything about and we're not asked about, so just leave that blank. The initial speed is 540 meters per second. The final speed is 670 meters per second. The acceleration is question mark, that's what we're trying to find, and the time is 7 seconds. So then you have to choose an equation of motion. In this situation, we don't know S, so I'm going to go for V equals U plus AT. And then I've put in my numbers here in my data, and then simplified to get acceleration of 19 meters per second to 2 significant figures, and that's in the upwards direction. So a really big acceleration due to gravity, almost 2g in this situation, 2 times the acceleration due to gravity. Question B asks us to find the distance travelled by the capsule during the 7 seconds. So again, gone for up the way to be positive. S we're trying to find, U 540 meters per second, V the final velocity 670 meters per second, the acceleration we now know as well is 19 meters per second, and the time is 7 seconds. So we've got a lot of information here. So there's quite a few different ways that you could solve this this particular question. So you might have done it a different way, but you should end up with the same answer. So I've used S equals ut plus a half at squared, really because it means I don't have to rearrange the equation. It's got S as a subject already. I've put the numbers in, and S equals 4,200 meters. If you notice here, we're using the acceleration of the spacecraft itself, because that's the rate that it's accelerating at. We're not using the acceleration due to gravity. We use the acceleration due to gravity when anything is free falling, but in this instance, the engines of the spacecraft are causing it to accelerate. So the spacecraft has travelled 4,200 meters, just over 4 kilometers, in those 7 seconds. Finally, question C. So in this question, we're trying to find how far the capsule is from the rocket after 7 seconds. And we're assuming the rocket continues to travel upwards at a constant speed of 540 meters per second. This was the speed the rocket was traveling at when the launch escape system was activated. So I'm going to make up the way the positive direction. S is what we're trying to find. The initial and final velocity, because the velocity is constant, is 540 meters per second. The acceleration is 0, it's not speeding up, it's not slowing down, and the time is 7 seconds. So I'm going to use the equation S equals ut plus a half at squared. And if you notice that this term here, the half at squared, will cancel. So we're essentially left with S equals ut, displacement equals velocity times time, which is a formula we're all familiar with. If there's no acceleration, then displacement is just velocity times time. So it's 540 times 7, which is 3,780 meters. So the rocket's travelled 3,780 meters, the capsule travelled 4,200, so the difference between those two values is 420 meters. So the rocket, I think, exploded approximately 10 seconds or so after the capsule left, so it would be well away from the rocket, and the crew should be safe at that stage when the rocket exploded. Okay, final part of this video then. So in higher physics, you will again meet what are known as open-ended questions. These questions always start with the phrase using your knowledge of physics. You should be familiar with these from the National 5 course. When tackling these questions, it can be useful to make some bullet points of the areas of physics that might be included in your answer before you start answering the question. You don't receive any marks for your bullet points, but it might help you to structure your answer and decide what's going to be relevant. And your answer should be written in complete sentences. Always remember that the questions are assessing your knowledge of physics, so try and remain on topic. So here's an example for you to try. Here's our open-ended question. So, using your knowledge of physics, comment on the launch escape system included in the SpaceX Dragon spacecraft. So, I've got some hints here just to give you some ideas, but there are lots of other areas you could discuss in your answer. So you might want to discuss how the system operates in terms of forces at each key point. So when the launch escape system is first deployed, you could look at the acceleration, when the parachutes are deployed and it decelerates, and when it splashes down into the water, each of these stages. You might want to think about Newton's laws of motion, for example. You might want to mention why it is included in the first place, any approximations we might have made in the questions on the previous slide, for example, the fact that we were saying the acceleration was constant, why and how the capsule is designed to cope with the large temperature differences. You should write your answer out in full and submit your answer to your teacher, who will be able to provide you with some feedback. These are usually marked out of 3 marks, and you usually receive 1 mark, 2 marks, or 3 marks, depending on the quality of the physics understanding that you show in your answer. So that's us at the end of this week's video. I hope you've enjoyed learning a little bit more about this feature of the SpaceX Dragon spacecraft. Now, really you need to continue practicing using your equations of motion. The more you practice, the more your confidence will improve, and you will find that you understand how to tackle these types of questions. Thank you.